Good evening, everybody. And thank you for the invitation to come back on what would be the 20th time, except for this pesky pandemic. So this is actually the 18th talk I've given you. The last one I gave you pre-pandemic was Fiat Lux, talking about the nature of light. And it doesn't matter if you didn't catch that one, it is recorded if you want to go and catch up later. This is about how our understanding of the nature of light allows us to build optical instruments. In principle, it could be telescopes or microscopes, but I'm going to concentrate on telescopes rather than talk about microscopes. So Fiat Lux talked about the nature of light and the colors of light. I gave demonstrations in which I measured the speed of light, measured the wavelength of light, looked at how colors of light can be split by prisms or diffraction gratings, and looked at the polarization of light. And in this talk, the first sequel, I'll be talking about how that impacts the way we use lenses and the way we use mirrors explicitly to actually make telescopes. So you could think this is a very useful way of categorizing telescopes from a cartoon from the site ACD. On the left, we have refractors. And the main disadvantage of using lenses in a telescope is that there is always color fringing, so-called chromatic aberration, or chromatic aberration, color fringing, color aberration, call it what you will. Reflectors instead don't suffer from that, but we are looking at reflections from a mirror. So if we're building a telescope using mirrors and we're always looking at reflections, of course the big advantage is we won't be able to see space vampires. So you could say, well, you've got to trade off one against the other. So this is The Vampire Strikes Back. This is episode 2 of Fiat Lux, The Vampire Strikes Back. So I will always be referring back to things that we found in Fiat Lux, but I'll try and explain what it was we found so you don't have to understand and don't have to have seen the original demonstration. But in the original Fiat Lux talk, I showed that when you send white light through a prism, it breaks it up into the colors of the rainbow, so-called dispersion. In other words, different colors behave differently. Different wavelengths of light corresponding to those different colors behave differently and take different paths through the glass. And hence, they split and end up with a rainbow. And that means we will have a problem. If we want to build a lens to focus light and actually produce images, regardless of whether it's microscopes or telescopes, we will always have this problem. And this is referred to as chromatic aberration or simply color fringing. You might want to get a nice round view of a star, but you'll have some horrible colors around it because not all the colors will be brought to focus at the same point. If we think of red, green, blue light hitting a lens, then you can see that if we think of the top and bottom of lens as a prism, in fact, all of the lens behaves a bit like a prism, but you can see most easily how the top and bottom parts of the lens sort of behave like prisms. You can see that red light and green light and blue light are not going to be bent through the same angles, and hence they're going to come to focus at different points. And so you will find that it's impossible to find one point at which you get the focus of all colors. So you might want to put your eye or your camera where the red comes to a focus, but then the green and the blue will be blurry and you'll get halos around the stars. And similarly, if you move to where the blue is focused, you'll find the red is out of focus. You can't find a unique point where red and green and blue are all in focus at the same time because of what's going on as the light passes through the lens. So this is just a cartoon which gives you an idea of what you would see if your actual object is, let's say, 4 dots. You can imagine this is just hypothetically, if there were 4 stars in the sky, what would they look like? Well, they would still appear as reasonably well-defined stars, but there would definitely be color fringing. For instance, there might be red on one side and blue on the other, or a red or a blue halo, depending on exactly what it is you're looking at. So there's the problem. How do you approach a problem with chromatic aberration? If light going through a piece of glass will always break up into a rainbow, does that mean that any optics you build out of glass will always suffer from chromatic aberration? What are you going to do about it? Well, there's 2 ways of thinking about the problem. One is to figure out how to fix it. In other words, how are you going to deal with chromatic aberration? The other is ignore it. In other words, lenses are not good for making images because you will have chromatic aberration, so don't use lenses. Avoid the problem by doing something else. And the first approach was not taken very seriously. In other words, it was figured out that, well, we'll always have that problem, so that there is no fix. And Newton basically said, well, you can't have refraction, you can't bend light, you can't focus light, unless you've got dispersion, in other words, separation of the colors. So if Newton says that chromatic aberration, Ca for short there, if chromatic aberration is inevitable, and that's what Newton says, then there's no point in fighting Newton, so we basically just throw away the idea of using lenses. We need to find something else. So the second approach, rather than trying to fix the problem, because Newton says it's unfixable, let's avoid the problem by using mirrors. And so the idea of building telescopes with mirrors, we know that Newton was one of the first to actually propose and then build a model of a reflecting telescope, and that gets around the color fringing problem because you're not using a lens to make the primary image. And that continued well into the 18th century. But eventually it was realized that there are ways around this color problem. You can't ever stop pieces of glass from splitting light into the various colors, but you can be clever about how you put bits of glass together. In particular, you can find glass with different so-called refractive index, different abilities to bend and different ability to spread the colors of light. And different types of glass with different density have different optical properties. And if you measure those optical properties and you're very clever about it, you can arrange it so that when the light passes through the lenses, it passes through the lenses, the two lens elements of different densities, of different refractive indices, such that when they actually arrive, and let me blow that up a bit so you can see it, the red and the blue actually arrive at the same place. In other words, the red and the blue are brought to the same focus if you use two lenses. Unfortunately, green is sent to a different place. So you still have a problem that if you focus, for instance, where the green is, you'll get a purple halo around your stars because the red and the blue won't be properly focused. So you still have the problem, but the problem is reduced. If you have two lenses, you can play with what different density of the lenses and what different curves am I going to make the lenses out of, and you can arrange it so that the red-blue problem goes away, but you still have a green problem. And then somebody figured out, aha, what if you had three lens elements, three lenses back to back? Again, if you choose the lenses correctly, if you choose the curvature of those lenses, you can arrange it so that red and green and blue all come to a focus. So in other words, you can effectively not get rid of the divergent color problem. You can see that within the lenses, the colors, the red and the green and the blue are going all over the place, but you can arrange it so that when they eventually come to focus, they all come to the same focus. And therefore, you can start to produce lenses in microscopes or telescopes that don't suffer from chromatic aberration. So it does take a bit of work. These so-called achromat, or in the case of 3, apochromatic, that just means even better color correction. Achromat means some color correction. Apochromat means even more color correction. So with 3 elements, as long as you're very careful as to how you make them, it is possible to bring red and green and blue to the same focus and hence get rid of color fringing. But it took a couple of centuries after Newton for people to realize that this was possible. That color is always a problem in a lens, but you can effectively correct one lens with another lens. And just as a little bit of an aside, these days, any camera optics or telescope optics, if they're made of glass, they will be made of a number of different elements. One of the elements is a mineral called fluorite. It's a calcium fluoride, and it's a low dispersion. Low dispersion means it doesn't spread the colors out too much, so it's easy to correct. So fluorite lenses have very low chromatic aberration. And if you're willing to spend enough money on camera lenses, you can buy camera lenses that have fluorite elements that minimize color aberration. So Canon, for instance, use fluorite lenses. On their more expensive lenses, they will use fluorite, which is an expensive thing to actually cast and make into lenses. So you don't tend to get them in your phone cameras, but if you spend hundreds or thousands of pounds on a camera lens, they will come with these fluorite elements. That's what Canon decided to do. Nikon took a slightly different route. They use a material called extra low dispersion glass, not a fluorite as it happens, but a different mineral with, again, very low dispersion, so-called extra low dispersion properties. And perhaps you've noticed, maybe you don't care unless you're a photographer, but whenever you see people on the space station taking pictures of Earth, they always use Nikon lenses. That's not because Nikon lenses are better than Canon lenses, it's because Canon lenses use fluorite, and fluorite is a relatively fragile mineral. And remember that when you go up and you blast off and when you re-enter the atmosphere, you'll suffer a lot of vibration, and it was thought that Canon lenses may suffer because of the fragility of the fluorite, so NASA decided to use Nikon lenses through most of their photography. So in addition to using lenses with intrinsically low levels of chromatic aberration, in other words, choose your glass so that it doesn't spread the colors too badly when the white light goes through the glass. Another possibility is don't make lenses with surfaces that are simply sections of a sphere, which is by far the easiest thing to make, and I'll come back to that point in just a second. In other words, if you use so-called aspheric lenses, if you use lenses with a shape that's not part of a sphere, you can actually focus light in clever ways and get rid of a lot of aberrations that would otherwise occur. So when you look at telescopes, for instance, you probably can't read it from where you are, but around the edge of telescopes, it often says either achromat or apochromat. In other words, is it partially color corrected or is it fully color corrected by combining different elements together to get rid of the aberration problem? In this particular case, what is this? This is a triplet. So these are three lenses made of different pieces of glass that will minimize the color aberration. And if money is no object, you don't have to stop at three. This one appears to be a quintuplet. So you can definitely get quadruplets, and you can get quintuplets. 5 lenses which are all correcting each other's color aberration. The problem is the more glass you add, you may be correcting the color problems, but you're absorbing a tiny amount of the light. And with a telescope, that's a problem. With a microscope, not quite as much. You just throw more light at the problem. But with a telescope, trying to pick up as much light as possible from a distant object, you don't want to add any lenses that aren't necessary. So people will choose to make telescopes with either 3 or 4 or 5 elements that will minimize the color problem of sending light through a piece of glass. This is what a camera lens looks like if you were to take a camera lens and a big saw and cut it in half. I don't suggest you try this at home, but if you take a camera lens and cut it in half, you can see that in this case, this I think is a wide-angle lens. You can see the number of pieces of glass in there is huge. It's not one piece of glass at the front or 2 or 3 pieces of glass and maybe one at the back. If we deal with it schematically, you can see that there are a very large number of pieces of glass, some of which are this so-called extra low dispersion, minimizing the color aberration, and some of them are quite definitely elements in which the surfaces have been ground to non-spherical shapes to try and minimize aberrations. But still, there are, a dozen or so pieces of glass in there. Every piece of glass is trying to remove the aberrations of the imperfections of the other pieces of glass. So it is a highly technological solution to a problem of light going through glass will split into colors. It's a very technological, very expensive way of dealing with the problem. In Fiat Lux, we looked at how waves behave because the nature of light is such that you have to understand how waves behave, and particularly how when 2 waves arrive at the same place at the same time, they will either add together if the 2 crests of the wave line up, or they will cancel each other out if the crest of one wave meets the trough of another wave. This is so-called interference. And here we have this hypothetical situation of one wave which is static and another wave which is moving, and the sum of those 2 gives you this result. Occasionally a much bigger wave when they coincide and add together, and occasionally that wave disappears completely when the crests of one line up with the troughs of another. So that particular phenomena of interference is crucial to how we want to design something such that we get a nice clear image of an object, again, regardless of whether we're talking microscopes or telescopes. If we have a glass lens or indeed a mirror, it doesn't really matter which, if we put color aberration behind us and say we can deal with that, if we're dealing with lenses or mirrors, then we have to make sure that when light arrives at the focus, all the light waves arrive in phase with each other, all the crests lined up, all the troughs lined up. Otherwise, if a trough of one wave lines up with the crest of another, we actually get cancellation of the waves, and we don't want that. We want all the waves that are coming to a focus produced by a lens or a mirror to add up. We want them to reinforce each other, not cancel each other out. So we have to worry about the phase of the various light waves that are coming to a particular point. Who hasn't done this? Who hasn't in their earlier days put two drawing pins in their desk and put a piece of string around them and a pen, and then keeping the string taut, move the pen in whatever shape you get? What shape do you end up with? Well, the clue's in the title there in the top right, yes. If you keep the string taut, wrapped around two drawing pins, then you will map out an ellipse. This is a rather important result. It may be fun to do, and you may think, so what? But the string, it can't work with elastic. You must work with string, and you must keep the string taut. That means that the string is always the same length. Doesn't matter what the length is, but it's always the same length. And if we take those dots and just forget the dots and just treat it as a shape here, we see these 2 points where the drawing pins were. They are the so-called foci, one focus and the other focus, or plural foci if you prefer. So that means if we were to think about the length of one of these lines drawn from one focus to the edge and then back to the other focus, remember how we constructed this in the first place? We constructed this with a piece of string whose length doesn't change. The distance between the two foci doesn't change within this particular ellipse. That means if I were to walk along any of those black lines from one focus to the other focus, I must walk the same distance. Because remember, we made it with a piece of string which isn't stretching. So all of those black lines, it doesn't matter which bit of the blue outline I hit, I can take any path I like from the focus to the blue back to the other focus. They will always be the same length. And that means if they all have the same length, then if I imagine sending light from one focus to the other focus, they all arrive in phase because they're all traveling exactly the same distance. It's not like some light rays are traveling a short distance and some light rays are traveling a slightly longer distance. They must all be the same distance. And if they're all traveling the same distance, they're all in phase with each other, which means we can use the shape of an ellipse to focus light, and it will guarantee that the light is precisely focused for us. So in other words, if we take this situation and say, well, let's make a mirror, not the entire ellipse, let's just take part of the ellipse and make a mirror in the shape of that ellipse. If I think about light being generated at one focus, okay, that's not very environmentally friendly. Let's take a low energy bulb, that's better. So we've got a low energy bulb generating light, and we can think about that light hitting the mirror and then coming to the focus. And all light hitting any part of that mirror will all come to a perfect focus, because the length of travel, the length that the light has to travel from the source to the mirror to the focus is exactly the same, regardless of which bit of the mirror I choose to hit. So an elliptical mirror will focus perfectly from one focus to the other focus. If you make the mirror perfect, okay, you can never make anything perfect, but if you could make a perfect elliptical mirror, it will take light from one focus and bring it to a perfect second focus. How does that help us? Because, well, okay, normally we're interested in a microscope, that might work fine, but in a telescope, the light isn't coming from 0.5 meter away or 2 meters away, it's coming from 1,000 light years away or 1 billion light years away. In other words, this second focus isn't in the telescope. The second focus that we're interested in is the source of the light. What happens if we stretch the ellipse? In other words, what we want to do is to take that focus and we want to move that focus to Alpha Centauri or the Andromeda Galaxy or something a long, long way off. if we take an ellipse, keep one focus fixed, but drag the other focus a billion light years away, what shape do we end up with? In other words, what shape do we get if we take an ellipse and stretch it an infinite amount? And that might sound like an impossible question to answer, but in fact that's an easy one to answer if you're a mathematician. What shape does the ellipse become? The ellipse becomes a parabola. In other words, if we think about a circle, both foci are in the middle. In other words, you tend to think of a circle just having one focus. It's in the middle of the circle. Technically, there are two foci, one on top of the other. If we separate the two foci and move one focus away from the first, we get an ellipse. The further we move that second focus, the more stretched the ellipse becomes. But what do we get when we stretch the ellipse by an infinite amount? We end up with this red line here, which we call a parabola. So a parabola is the limit of what an ellipse is if you were to stretch it until the two foci are separated by infinity. So if they're separated by a finite amount, you have an ellipse. If they're separated by an infinity, you have a parabola. And there are other curves beyond those, beyond the parabola, which I will say something about. But we're talking about conic sections. Maybe you remember this from school, maybe you don't. But if you take a cone and slice it horizontally, you get a circle. If you take a cone and slice it at an angle, you get an ellipse. If you take a cone and slice it at an angle which is the same as parallel to one of the sides, you get a parabola. And if you slice it at a bigger angle, such as vertically, for instance, you get this other shape called a hyperbola. So circles and ellipses and parabolas and hyperbolae are all conic sections. They all sections of a cone, and they only differ in how stretched they are, if you like, which is a function of how you've decided to take those sections with different angles. So when we think about it, the curves that define what shapes are good for focusing, for instance, ellipses or parabola, if we're interested in focusing an object from an infinite distance away, these are also the same shapes that define how objects move around the sun. We can think about the Earth going round the sun in a circle. Kepler and Newton told us, well, actually, the planets go round the sun in ellipses. The maths is the same, which is why we get the same results. The curves that are good for focusing are the same as the curves for how do things move in a gravitational field, because when you boil it down, the maths is effectively the same, and hence you get the same set of solutions. So planets, it was found, follow closed elliptical orbits. So there's a couple of foci. The sun is at one focus. The other focus is nothing. It's just empty. There's nothing actually there. So the sun is one focus, and the planets go round the sun in ellipses. If something drops into the solar system from way out into the Oort cloud, if something is just dropped from the Oort cloud, it will come zooming into the solar system and go round the sun in something that closely resembles a parabola, the limit, if you like, of taking those two foci and separating them out. If something comes into the solar system at speed, in other words, it isn't just dropping in from the outer reaches of the solar system. If it comes hurtling in from somewhere else, like in 2017, that odd-shaped asteroid, that asteroid came in 2017, and that followed a hyperbolic orbit because it came in at speed, went past the sun, and left the solar system, and again is going to escape from the solar system. So Oumuamua is on one of these hyperbolic orbits. So it's interesting to note, but not necessarily useful, that we can build telescopes with the same curves as the curves that dictate how planets move around the sun. So if we've taken our two foci, and we know that elliptical mirrors take light from one focus and send it to the other focus, if we separate those two foci, so one focus is in our telescope and the other focus is in Alpha Centauri or somewhere else, then a parabola should focus perfectly. In other words, starlight from a focus at infinity is effectively parallel, as close to parallel as makes no difference. So parallel light coming in and hitting a parabolic mirror, so the parabola is shown in grey, and of course we're actually choosing to make our mirror out of a small section of that parabola. So starlight from infinity should come to a perfect focus if we use a parabolic mirror. So if parabolic mirrors are the correct shape, if they're the ones that we should use to focus perfectly from a distant object, why is it that sometimes you see telescopes are occasionally made with spherical mirrors? Rather than parabolic, rather than elliptical, they're made with spherical, i.e. the section part of the surface of a sphere. Well, simple answer as to why some telescopes use spherical geometry: they're easier to make and they're cheaper to make. If you think about taking a couple of pieces of glass and actually grinding a mirror, if you take two slabs of glass, which are both flat, it doesn't really matter what shape it is, let's imagine they're pancake shaped, you're taking two bits of glass with two flat surfaces. If you take those two surfaces and you, with a little bit of abrasive material in between them to make sure you're grinding the surfaces away, if you move that backwards and forwards and backwards and forwards, what possible shape are you going to make if you apply a little bit of pressure on that top piece of glass relative to the bottom piece of glass? Well, in principle, if you're applying perfectly uniform pressure, it'll stay flat. But if you apply a little bit of more pressure at the edges, what you will end up doing is generating a curve. And what is the only curve that will stay in contact with itself if you move these pieces of glass backwards and forwards? The only shape that will work and stay in contact is, in this case, a circle, or in 3 dimensions, a sphere. So you must generate a spherical surface if you move one piece of glass over another and allow one to wear down the other. You can't make any other surface. You can't make a parabola, you can't make a hyperbola, you can't make an ellipse, because at some point they would lose contact with each other. A sphere is the only object that looks exactly the same if you rotate it. Everything else will look different. So if you move glass backwards and forwards, you'll end up with a spherical shape. And that's basically what all of mirror making is about. And that's why amateurs are quite happy to do this and make spherical mirrors. So anything beyond that, if you want to start thinking about, well, how do I actually make a parabola? It is much more difficult, because you can't simply let nature take its course. It's a lot more trial and error to try and make curves other than spherical curves. There are spherical telescopes out there. A very large radio telescope here in China called the 500-meter aperture spherical telescope. And it is literally a large, well, it looks like a wok, but it's actually a large spherical dish. And you can see that they've named it the 500-meter aperture spherical telescope. It's actually a radio telescope. But 500-meter aperture radio telescope, they decided that acronym was perhaps not the best one to go with. So yes, that will suffer from problems because it is not the correct shape to focus light, or in this case radio waves, from infinity. But it's easier to make spherical mirrors than it is to make any other shape. Spherical mirrors, or indeed spherical lenses, suffer from so-called spherical aberration. It's an aberration that is formed from choosing the wrong shape. Instead of choosing a parabola, if you choose a sphere, things will not focus correctly. At first sight, it doesn't look too bad, but notice that light hitting different parts of the mirror are not brought to the right focus. Light hitting the center part of the mirror is focused at one point, but light hitting the edges of the mirror are brought to a focus prematurely, some distance in front. So light from different parts of the mirror will not focus at the same point. That is characteristic of a spherical shape, regardless of whether it's a spherical mirror or a spherical lens. We can take away the light, take away the mirror, replace it with the lens, we still have the same problem. If you were to generate a lens with spherical surfaces, it will not focus correctly, because the light hitting the outer part of the lens, in a sense, the outer part of the lens is too strong. It comes to a focus too early. So instead of getting nice pin-sharp images of stars, what we actually see is we can't find anywhere where all the light is coming to a good focus. We can find some regions where most of the light is focused, but then we get a horrible halo of defocused light coming from different parts of the mirror. And this is precisely the problem that the Hubble Space Telescope had when it was first manufactured. So instead of getting nice sharp images of these round dots, hypothetically, we would get these rather blurry dots with a little bit of a halo around each of them. And if you think about what that means in terms of trying to observe something, instead of getting a nice sharp view of Saturn, we would get what looks like it doesn't look like it's properly in focus view of Saturn, which is precisely what it is. You can't get all the light to focus from all parts of the mirror. We don't seem to have that problem. If your eyesight is good, or at least if your eyesight is bad but corrected by spectacles, generally speaking, you don't find that when you look at a point of light, it seems to be surrounded by a horrible halo. Well, that's because evolution is wonderful. Evolution has given us a lens which is more dense in the middle and less dense towards the outer part of the lens. That means that all the light comes to focus. Remember, the problem with spherical aberration is the outer part of the lens is too strong and it comes to focus prematurely. But if the material in the lens is less dense, lower refractive index, that takes that into account, and all light, regardless of where it hits the lens, will come to a focus on your retina, or at least once you've got your spectacles correct, it will come to a focus correctly. And that is purely the result of evolution. If we started out with lenses that were uniform in density, we would suffer from spherical aberration. And over a few million years or more, that has disappeared to the point where evolution has provided us with spherical aberration-free optics in our eyes. But what do you do about this? With color aberration, we said, well, if you're clever, you can put different lenses together and get rid of color fringing or color aberration. But what about spherical aberration? If you build yourself a lens which doesn't focus correctly, what are you going to do about it? Well, the solution was rather drastic. Don't let the light through the edges of the lens. Only let the light through the center of the lens. But that means you're throwing away all of that beautiful bit of glass. You might have made yourself a large lens, but you're only looking at the light that's coming through the center of the lens, and you're throwing away perhaps 90% of the light. So that's not really desirable, but that's the way around the problem. If you know that you're going to have this particular aberration, you try and minimize the problem by making your lens relatively small compared to the focal length. The smaller the lens compared to the focal length, the less this is a problem. It's a real problem when the lens is large and you're having to worry about the light hitting the edges of the lens. But if you keep your lens small compared to the length, or the length of the telescope, or the focal length of the optics, then you can minimize the problem. And that's why we ended up with telescopes that looked like this. Hevelius is down here somewhere, and the eyepiece is here, and the objective lens is somewhere up there. And these are not lenses, these are just apertures on the way. So you can imagine how easy it would have been to use a telescope like this. A tiny lens, I don't know how many tens of meters away from the eyepiece, and the whole thing suspended on ropes and then lifted by people pulling on ropes and trying to move it around. As the Earth spins, the sky seems to rotate and the stars seem to move. Can you imagine the difficulty in trying to follow an object with a telescope like this? Hevelius said it was easy to use. Halley said it was useless, so there's a slight difference of opinion there. But basically, that was one way of getting rid of the aberration problem, but it led to all sorts of problems in terms of actually usability of the telescopes. So you think, okay, lenses have all sorts of problems. What about the idea of using mirrors? Newton had the right idea. Use mirrors gets rid of the chromatic problem. You still have to perhaps make the mirrors the right shape. You have to think about, do I want to make this mirror a parabola to make sure it focuses correctly rather than a spherical mirror? But at least you can get rid of the chromatic problem dead. So what combinations of mirrors could we use to allow us to construct a reflecting telescope? If we wanted to make a telescope but not using a lens to make the primary image, what options do we have? Well, the preferred option is a parabolic mirror. Light comes from infinity and comes to a focus. But if we want to look at what that image is with an eyepiece, our head literally would get in the way of the light, and most of our head would block most of the light coming in. So we want to be able to inspect what that focus is like, but we don't want to put our head in the way. So Newton said, okay, that's fine. We just add a flat mirror, a 45-degree flat mirror, and send the light off to the side. And then we can use an eyepiece. Yes, an eyepiece is usually made out of glass, and so it will have its own chromatic aberration, but being a smaller piece of glass, it's easier to grind it the right shape with the right materials, and it's easier to minimize chromatic aberration in an eyepiece than it is chromatic aberration from the main objective lens forming the image. So that's how we would use a Newtonian telescope, a parabolic mirror, and a flat to send the light off to the side. And that's why we see classic Newtonians like this, a tube, and then on the side we have the eyepiece. There's a little telescope there just to help us point it at the right place. But here's the eyepiece on the side at right angles to the tube itself. Hereafter, I'm not going to draw the eyepiece. I'm just going to think about how the mirrors are used to make the image. In all cases, that will either end with a camera or it'll end with an eyepiece placed at that position. So that's a Newtonian telescope, which is quite popular amongst amateurs. What alternatives do we have? Well, we can bring the light to a focus, and remember where we started. We started by saying if we draw an ellipse, we can show that light from one focus can be sent to another focus using an elliptical mirror. And that's this particular design from Gregory, a Gregorian telescope. You let the light come to a focus, and then you use an elliptical mirror to take that light from one focus and send it to a second focus. So you have an elliptical mirror, and you let the light go to a second focus. In this case, it's a focus on the other side of the primary mirror. Okay, yes, you have to put a hole in the mirror. That's one downside, but putting a hole in the mirror isn't quite as drastic as it sounds. That's fine. So this elliptical mirror here is designed to take the light from the primary focus and send it to a secondary focus comfortably behind the main mirror, and so you end up with a telescope which looks, in the conventional sense, rather than having an eyepiece on the side, you have an eyepiece at the back of the telescope. And it has the advantage that you have a relatively long focal length that is condensed into a relatively short tube. So this is the so-called Gregorian design involving two mirrors, parabolic and elliptical. But neither of these mirrors are easy to make. That is part of the problem. Yes, in principle, you can make any shape mirror you like, but it is tricky. And Gregorian telescopes tended to be quite small because it was difficult to make the right shapes large enough. Another popular design of the times was a parabolic mirror, and instead of letting the light come to a focus and then letting an elliptical mirror send it from one focus to another, you intercept the light early. You intercept the light before it reaches focus. And I'm not going to talk details, but a different shaped mirror, in this case a hyperbolic mirror, will take light that would have come to one focus behind the mirror, and you send it to another focus in front of the mirror. That's how hyperbolic mirrors work. So a parabolic main mirror and a hyperbolic secondary mirror gives you a very long focal length in a short tube, which is again very nice. The downside is you've got some difficult shapes to make for your mirrors. But it is one of the most popular types of telescopes, the Cassegrain design, using two mirrors. Now, for amateurs, we're always on the lookout for, yes, but that's difficult to make and that's difficult to make. So how can we make this design cheaper to the point where amateurs can actually afford one, rather than it can only be made by gentlemen scientists who are independently wealthy and can afford to do this? Well, there is a design that came about in the middle of the last century in which the parabolic mirror is replaced with a spherical mirror. And remember, the main advantage of a spherical mirror is it's easy to make, it's cheap to make. You can mass produce them. You can put them on a production line and you can kick out spherical mirrors to your heart's content. Other mirrors take a lot more effort to make. So you can use a spherical mirror, but we know that spherical mirrors don't focus properly. They have spherical aberration. Yes, say the manufacturers, but I've saved so much money by making this spherical rather than parabolic, I can afford to simply add another little bit of glass that corrects for that spherical aberration. And what they do is put a piece of glass at the front of the telescope. It looks like it's a flat piece of glass. It is ever so slightly not flat on one side. One side is flat and the other side is ever so slightly curved, just enough to correct for the spherical aberration of the mirror. And you might think that's a rather tricky thing to make, but actually it's actually cheaper to make a piece of glass that's ever so slightly not flat than it is to try and make a parabolic mirror, which is a lot different from a spherical mirror. So these so-called Schmidt-Cassegrain designs, perhaps you've seen some telescopes that look like that. They are very popular amongst amateurs. They have a large flat piece of glass at the front, which is holding this mirror in place, and you can't really see, but it's a spherical mirror in the back of the telescope. So you can then get optics which are extremely good for relatively affordable amounts of money. In other words, these things don't cost hundreds of thousands of pounds. They might only cost many hundreds of pounds, or perhaps 1,000 or two or something. Just about affordable for those that are serious about astronomy. Another alternative was the idea that, well, let's keep the idea of spherical mirror because that's nice and cheap. Let's find a slightly different way of correcting the spherical aberration that exists in these telescopes. And somebody had the bright idea. That somebody must have been Mr. Maksutov, because that's where we get the name from. The idea is you put a slightly curved meniscus lens at the front. So the corrector plate is actually a thin piece of glass which is made to a particular curve, and the curve is designed to just correct the spherical aberration of the mirror. It also has the advantage that you don't need a secondary mirror. You just paint silver onto the corrector plate itself. In other words, you make this corrector plate just the right shape, such that by painting a little spot of reflective material like aluminium or silver on the glass, you actually get your secondary mirror as well. So that particular design is called a Maksutov, and it's characteristic of this concave lens at the front. So if you ever see a telescope and the front element appears not to be bulging out as you would expect in a refracting telescope, but if it seems to be inward, a concave lens on the front there, that's because you're looking at a Maksutov design. So you can start to recognize how the optics are put together simply by, as it were, inspecting the telescope itself. So there are lots of telescopes out there. It's an absolute minefield for any amateurs that are interested in buying telescopes. Some telescopes use various bits of glass, and they're called dioptric telescopes because they use lenses. Sometimes they're called refractors. And there's a whole load of telescopes that use mirrors, and they're called catoptrics because they use mirrors. From the original Greek. And of course, where they overlap, there are various telescopes that use a combination of mirrors at the back and bits of glass at the front. So these go by the rather cumbersome name of catadioptrics because they're partly dioptric and partly catoptric, partly lenses, partly mirrors. So telescopes that use both are called catadioptric. And basically, a lot of people simply abbreviate that to a cat. So if anybody says, yes, I've got a telescope, it's an 8-inch cat, what they mean is it's got an 8-inch mirror and it's that particular style, catadioptric, with a combination of mirrors and lenses. So, parabolic problems. We've said that ideally you want to use a parabola, but there are ways of using other lenses and getting around the aberrations that a non-parabola would give you. But there is even a problem, even with parabolic. A parabolic mirror will focus light from a distant object perfectly if that distant object is perfectly lined up with the mirror. In other words, if the light hits the mirror at effectively 90 degrees. So if you think of it, that mirror is facing an object. But if a light from an object off axis comes into the parabola, it won't focus correctly. I'm not going to demonstrate this, you'll just have to take my word for it, but if we were to take light hitting the mirror, then that would come to a perfect focus if the light is hitting it broadside, as it were. But if I were to tilt the mirror so that it represents light coming in off axis, then some of the light would be focused correctly, but some of the light wouldn't, and we would end up with an aberration. I'll show you what that looks like in just a moment. So if we're lined up on the center line, in other words, for instance, if we were to use a parabolic mirror and take an image, any star in the middle of the image should be perfectly focused and aberration free. But light coming from stars towards the edges of the field of view, they will get worse and worse and worse in terms of aberration because of this so-called coma. It's called coma because the aberration looks a bit like the stars end up looking like comets. In other words, instead of getting nice sharp points like this, we end up getting a sort of a tail, and I'll show you a real version of that in just a second. So it can be corrected. Coma can be corrected by adding. You can always get rid of aberrations by adding more optical elements. If your mirror has aberrations, you can get rid of it by adding lenses that correct for that aberration. In other words, you can buy a coma corrector which allows you to get rid of this aberration from parabolic mirrors. But wouldn't it be good if you didn't have that aberration in the first place? Is it possible to build something that doesn't have that aberration? Well, yes, at a cost. If you were to replace a parabolic mirror with a hyperbolic mirror, and if you choose it very carefully, you can deal with that. This is a particular type of design called a Ritchie-Chrétien design. So instead of having a parabolic mirror here, we replace it with a hyperbolic mirror. Hyperbolic mirrors are terrible in terms of trying to make them because they're such an odd shape. Amateurs will not attempt to grind a parabolic mirror. But these days it is possible for computers and computer numerical control machines to effectively make any shape you like. And therefore, if you want the best possible aberration-free optics, you will go for a hyperbolic mirror, which is similar to but a little bit flatter than a parabola, a hyperbolic mirror for the main mirror as well as the secondary. And that is precisely what the Hubble Space Telescope has gone with. The Hubble Space Telescope is a hyperbolic mirror of its primary and a hyperbolic mirror in the secondary. The catch was they made it wrong. It should have been a perfect machine, but when they actually made this mirror, they made it incorrectly. The test jig that they set up was set up incorrectly, and they produced this hyperbolic mirror the wrong shape. In other words, it was a hyperbola, but it was the wrong hyperbola. It was literally the wrong curve for the telescope. And they had to correct that with the various additional correction optics that they added in the next few years. And that, of course, is a different story, which I covered in the talk on the Hubble Space Telescope. The last really big telescope that used a parabolic mirror, in other words, it's almost a dinosaur now, but it's 70 years old. The Hale telescope is now about 70 years old. It was the largest telescope in the world when I was born. It was the largest telescope in the world when I was a kid. It was the largest telescope in the world for most of my adult life until the latter part of the last century, when it was overtaken by other telescopes. And it was the last big telescope that used a parabolic mirror. And that was partly because when Hale wanted this thing built, in the early part of the last century, he had a disagreement with Ritchie, he of the Ritchie-Chrétien design, who said, I can make a much better telescope if we made the mirrors hyperbolic. But Hale had cold feet. He didn't like the idea of going with newfangled technology. How on earth are we going to make a mirror this shape? Yes, in principle it ought to work, but Hale was more conservative. He would much rather have a parabola which worked as well as possible rather than stake his money on the possibility of hyperbolic mirrors giving him a better set of optics. So the limitation of having a large telescope, 5 meters in diameter, this particular mirror, so roughly the size of this room approximately, that meant that the telescope itself did indeed suffer from chromatic aberration because of a parabolic design. In principle, you could add lenses to correct for that, and when you look at some of the images it produced, bear in mind that the Hale telescope was designed for scientific purposes. It was not designed to take pretty pictures. It was designed to get information about nebulae and stars and distant galaxies and galaxy clusters. So it did occasionally take pretty pictures as well, the Horsehead Nebula here. And one of my favorite planetary nebulas, a star that exploded, that star effectively shrugged off its outer atmosphere many years ago and produced this planetary nebula. I'm not showing it for that astrophysical reason, but I'm showing it because this is one of the few photos that I could find that actually demonstrate that the Hale telescope did suffer from chromatic aberration because it had a parabolic mirror. The stars at the center are perfectly sharp and well formed, but look at the stars at the edge. You can't see, so I'll blow those stars up. They are not stars. They are coma or chromatic aberration. They are looking more like comets. These should be pinpoints. There's no reason to assume those objects are anything other than stars, which should be pinpoint objects. But because the light is coming in off axis, and because a parabola will focus perfectly at the center but imperfectly at the corners, then you can see this chromatic aberration. Not a problem in the sense that if you're trying to study this particular nebula, it doesn't matter if there's a little bit of distortion in the corners. And if you are worried about that, you add some optics to correct for that. But most of the time, Hale was interested in looking at, for instance, a distant galaxy, which would have been exactly where the telescope was pointing. You don't study a galaxy by getting it in the bottom right-hand corner and hoping you get a nice image of it. You make sure it's centered in your field of view. So parabolic, not used for basically since the middle of the last century. So where is state of the art now? What do people tend to use? Well, many research telescopes either use the Ritchie-Chrétien design, like, for instance, the Hubble Space Telescope, but the very latest ground-based telescopes actually have a different approach, and that is not to use just two mirrors, a main mirror and a secondary mirror. They actually use three mirrors. Remember chromatic aberration, color fringing in lenses. You can correct it to some extent by having two elements in your lens. You can correct it almost perfectly by having three elements in your lens. It's the same sort of idea. If your optical system has some aberrations, add another mirror and carefully make sure the curvature of each of the mirrors is such that any aberration is cancelled out to give you a lovely field of view. And that's what's happened in this particular design. It's called a three-mirror astigmat, meaning aberrations have effectively been eliminated over a huge field of view. And huge doesn't mean many arc minutes, it means many degrees. A chunk of sky much bigger than the full moon can be imaged by this telescope, and it is perfectly sharp, corner to corner, even though the CCD detector for this particular telescope is not like the Hubble telescope detector, which is about 4 centimeters on a side. The detector on this telescope is not 4 centimeters on a side, it is about the size of a coffee table. 3 billion pixels in this detector, and it is sharp corner to corner, absolutely, because this particular three-mirror design has been designed carefully to make sure that these errors are eliminated. That particular telescope, I decided to make that telescope the subject of Fiat Lux II, which you may or may not be interested in at a later date. It should be coming online before too long. It was supposed to be operational by now, but COVID sort of put a kibosh on that. So maybe next year or the year after, this new telescope will be coming online, the so-called Large Synoptic Survey Telescope. It's since been renamed, but that's the most descriptive name that we can use. So I'm not going to say any more about that, other than we've moved away from just having a hyperbolic mirror and a second hyperbolic mirror to make sure that we focus correctly. So we said earlier that telescopes have used circular or elliptical or parabolic or hyperbolic shaped mirrors for focusing, but some don't bother doing that at all. The mathematics tells us that these particular shaped mirrors will focus the way we want. In other words, we can sit down, and it's not necessarily easy, but we can do the maths and we can figure out that yes, this particular shape of mirror will do the job. In other words, people can work out that that's the right answer. But a different approach which is now being adopted is, in some cases, for instance, a particular telescope that's currently being built in the high Andes, they are designing the mirrors by getting a computer to tell them what is the optimal shape for the particular lens that's going to focus the light for us. You're not restricted to only having circles or ellipses or parabola or hyperbola. Basically, you can tell the computer, I don't care what the shape is, just pick a shape that gives us exactly what we want. And you have to have a certain trust, because effectively the computer then designs the shape of the mirrors. They are no longer something that you can recognize as, well, that ought to work because I know how that particular shape focuses light. We're moving away from conic sections to effectively computer designed as well as computer manufactured mirrors. So let's keep our fingers crossed that it does work the way it's supposed to. In Fiat Lux, I was talking about the wavelength of light, and I actually measured the wavelength of basically a red laser like this one, and determined that that red laser appears to have a wavelength of somewhere between 600 and 700 nanometers. If we want light to be focused correctly, let's imagine we're just talking about the visible part of the spectrum for the moment. So we're talking about wavelengths in the range of 400 to 700 nanometers. If we want to get a perfect image, or as close to perfect as we can get, we want all the light to arrive at the focus such that there are no errors more than a fraction of the wavelength of light. If different parts of the mirror are slightly high or slightly low, then the path length for the light reaching the focus from the mirror will be different, and we'll start to get cancellation of different waves. So if we want none of that, if we want all the waves to arrive in phase, we can't afford to have any bumps or lumps or bumps or peaks or troughs in the mirror shape that are significantly bigger than hopefully a small fraction of that wavelength. So in other words, we would like the bumps to be certainly smaller than 100 nanometers in size in order to make sure that everything is focused correctly. And it is possible to do that. With modern computer numerical control machinery, it is possible to grind mirrors with surface deviations, in other words, mountains and valleys, bumps and troughs, that are somewhere of order 20 to perhaps 30 nanometers. It is possible to get that sort of level of smoothness in a mirror that is many meters in diameter. And it's difficult to judge what does that mean in terms of smoothness. So let me just sort of give you an analogy. If we take a mirror and scale it up until the mirror is the size of the Earth, then how big would these lumps and bumps be in the surface of the mirror? Well, they would be a few centimeters in size. So over something the size of the Earth, the deviations from the figure we want is no more than a couple of centimeters or so. That's the degree of accuracy, that's the degree of smoothness that can be generated on a mirror that's 6, 7, 8 or more meters in diameter. A rather incredible feat, something that would have been impossible, of course, before the design with computers and the manufacture with computer numerical control. Let me finish up with just a couple of points. In Fiat Lux, we saw the concept of interference of lots of waves gives us diffraction. Diffraction means that when we look at what is, we hope, a point of light at a distance, we won't see it as a point of light, we'll see it as a speck of light with a finite size. And in fact, there will be a bright central region around the star, and there will be some signs of diffraction rings. These little rings look like ripples around the outside. In other words, what should be just a point of light appears as a small disk of light with circles around it. This is a result of lots of waves adding together. When we have interference of lots of waves, we call it diffraction. And any set of optics will be limited by the rules of diffraction. The rules of diffraction say the larger your aperture, the larger your lens, the larger your mirror, the less you'll notice these diffraction effects, which is why we are always trying to make telescopes bigger and bigger. It's not just a question of trying to catch more light, it's also trying to minimize the effects of diffraction so we can see sharper and sharper detail, because the effect of getting a broadening of every point of light that we're looking at, that broadening will get less and less as we go to larger and larger mirrors. So larger lenses, always desirable, catch more light, and give us less diffraction problems. And let me finish just with a comment about Hubble and James Webb. Hubble Space Telescope, of course, launched back in 1990. James Webb Space Telescope launched Christmas Day last year. Substantial difference in size between these two mirrors, which you don't always appreciate unless you see them side by side. It's not just the size of the telescope that matters, it's the size of the mirror. So the Hubble mirror is about 2.5 meters in diameter. The James Webb is 6.5 meters in diameter. So yes, it will collect more light, but when you start to think, well, will it actually show more detail? Are we going to get a resolution of distant objects that is better with the Webb? Because we're dealing with a much bigger mirror, and so diffraction effects will be less for the same sized mirror. Well, they will for the same wavelength. If we are looking at an object with the same wavelength with the Hubble and the Webb, the Webb will give us higher resolution. But remember, the James Webb is working in the infrared. That could be a wavelength which is 10 times longer than the visible wavelength that Hubble is working at. And what matters when it comes to seeing detail is how big is the mirror compared to the wavelength of light that you're looking at. So if your mirror is 10 times bigger, well, it's not in this case, it's obviously substantially bigger, but if the wavelength is a lot bigger, you are not going to get a much higher resolution. So people that always claim that the Webb is going to give you a much higher resolution image than the Hubble are missing the point that yes, the mirror is larger and so is more sensitive because you're picking up more light, but because you're working generally at longer wavelengths, the resolution that you can obtain with the James Webb is probably going to be much the same as the resolution you get with the Hubble. If you look at any of the images produced by the James Webb and sit down with the Hubble next to it and look, you'll see that the resolution is approximately the same in both. They are different in the sense that, as we saw earlier with the demonstration, the James Webb is able to see through certain dusty environments and able to see things that the Hubble can't, but the resolution dictated by the diffraction limit is approximately the same for both of them. The James Webb is actually situated somewhere rather different from the Hubble. The Hubble is in orbit around the Earth, but the James Webb is parked at one of these mysterious so-called Lagrange parking points. There are 5 points in the solar system where you can park a spacecraft by basically taking it there and sort of just leaving it. And so James Webb is actually at L2. Lagrange points are something I talk about in a different talk where I describe it as, well, it's not rocket science. Well, it is rocket science, but I try and take all the maths out. And James Webb is actually sitting there at L2, 1,000,000 miles above midnight. So midnight, of course, is this point here, furthest away from the sun, always. And James Webb is sitting 1,000,000 miles above that. So James Webb is always sitting 1,000,000 miles above local midnight on the Earth. It's there because it's nice and cold when it gets its sun shield in the right position, and of course it must be cold because it's effectively looking at wavelengths of infrared which would be affected by the heat of the moon, the heat of the Earth, the heat of the sun. So we have to keep all the instruments cool to make sure James Webb can see everything that it wants to see, such as amazing pictures like this one that came out not so long ago. The James Webb revisited the pillars of creation that was imaged by the Hubble soon after it was made. The Hubble imaged this in 1995, and James Webb has gone back to the same thing to show what a wonderful instrument it is. It had to mosaic again quite a few different tiles in order to make an image this large. So by working in the infrared, it's doing different things to the Hubble. It's able to see things that you wouldn't be able to see if you were only looking in the visible. It's hoped to be able to study early star formation, exoplanet formation, and because it's working in the infrared and because very distant objects, because of the expansion of the universe, are redshifted quite often away from the visible to the infrared part of the spectrum, that's where James Webb will be working, and so James Webb ought to be able to see very distant galaxies as well as what's going on in these very dusty environments. So let me just finish with an indication of how telescopes have changed over the years. Here's a timeline from Galileo's day up to the present day, and the vertical scale is the size of the lens or the mirror in various telescopes, a few representative dots here showing you how telescopes have grown in size over the years. The blue dots are refractors that are basically just lenses at the front. The other colors, orange, green, and red, are different ways of making reflecting telescopes. You can either make them out of metal, or you can make them out of glass and put a thin coating of metal on the top, or you can make them out, instead of making them out of a solid piece of glass, you make them in segments, like the James Webb mirror, for instance. You make them in segments and put lots of segments together to make larger mirrors. So perhaps you can figure out what's what. The first thing labeled G, that's Galileo's first telescope. The first mirrored telescope labeled N is Newton's little 1-inch mirror. And you can see that refracting telescopes got larger and larger, but then they went down because achromat and apochromat lenses were more difficult to make. So although they were color-free, you couldn't make them the same size, and so you started with smaller lenses, and then eventually they started to grow into much larger telescopes. But by then, metal mirrors were being used, and we have telescopes such as the one from Herschel here, the 40-inch telescope, the Leviathan of Parsons Town over in Ireland at Birr Castle. The largest refracting telescope there, that's about as big as you can make a lens. 1 meter in diameter is about the largest lens you can make, simply because if you make a larger lens, it will start to sag under its own weight because you support it at the edges. You can't really support it in the middle, unlike a mirror, which you can support from behind. So lenses basically topped out at about 1 meter. That's the Yerkes 40-inch there. RC is simply a label that says where the first Ritchie-Koreshian mirror was made. Up here, H, we have the Hale telescope, a 5-meter mirror. And on the extreme right here, we have the LSST, the Large Synoptic Survey Telescope with an 8-meter mirror. And right at the top here, a segmented mirror, the European Extremely Large Telescope with a whopping 40 meters diameter and a focal length of about 3/4 of a kilometer. So that is a much larger telescope. But you can see that very roughly we're on an upward trend, and who knows where we will be. Perhaps in a few more decades, we might hit the magic 100-meter aperture telescope at some point in the future. So I've been telling you how lenses always have chromatic aberration, but you can deal with that if you're clever about the way you put lenses together. When you're dealing with mirrors, you have to ask yourself, how do we ensure that all the light comes to focus? How do we ensure that all the light ends up in phase? And we can do that by thinking about elliptical mirrors or parabolic mirrors or hyperbolic mirrors. If we use spherical mirrors, we end up with aberrations, but we can, if we're clever enough about making the shapes of mirrors, we can deal with that. And the laws of physics specify that the amount of detail that you can see is determined by the wavelength of light and the aperture of the lens or the mirror you're using, and hence there's this aperture fever, always wanting to build larger telescopes so we can see fainter objects and ultimately see more detail in those objects. And that aperture fever, I'm sure, will continue for decades to come. Thank you for listening.